Good afternoon, everybody. Welcome to our lunch hour seminar of the Ottawa Regional Centre for the Canadian Meteorological and Oceanographic Society. This is a series of seminars that we conduct from September to November and January until April. And today it is my great pleasure to introduce Professor Ariya, Parisa A of McGill University. And her topic is listed here. I needn't read it. It is also on our CMOS website in a slightly different version with a nice abstract and a bio sketch. But by way of introduction, I would note that Parisa is the James McGill Chair in the Department of Chemistry and Atmosphere Ocean Sciences at McGill, and she has served as Chair of the Atmosphere Ocean Sciences. She's also served as editor of several reputable science journals, and her expertise and advice are really highly respected in Canada and abroad. She's contributed to many policy-related activities. Just to give a few as an example, one on toxic contaminants, one to the Canadian Environmental Protection Act group, the Clean Air Regulatory Agenda she's contributed to, and her expertise has been sought in Arctic assessment programs and projects. So, and many others, and you can read them in the bio sketch. Parisa is kindly consented to talk to us today. She heads a large graduate research group that bridges between atmosphere and ocean sciences and chemistry, and is very vibrant and active at McGill. So without further ado, I will pass the mic over to Parisa. Welcome, Parisa.
Thank you very much for your very kind invitation, and also you were very kind to me for over the years, and I appreciate that. I would like to start with saying that what I am going to be talking to you today are the small particles, nano or micro size, that are actually the big elephant in the room in the case of the climate change health sciences. And I will be showing towards the end how the technology that we develop for them, a purely Canadian technology, can actually address the challenges, many challenges of air quality, climate change, and health, and has a potential to be part of the solution. So, as always, I would like to let you know where I'm going. I'm going to make something that is totally dark and invisible, show you how we can make them invisible, but not just by seeing them, seeing these nanoparticles, optically speaking, but I will be able to show you that we can address some major IPCC and WHO regarding their surfaces, physicochemical processes, four-dimensional size, four-dimensional time, 3D plus time, as well as phase and intensity, contact angle, and so forth as well. And the technology that is based on optics, physics, chemical processes of surface, as well as the artificial intelligence, can have much more potential for health, for imaging, as well as sending items to satellites. So what I am doing and introducing is how we actually had the process to reach the capability to address these challenges in air quality, health, and climate. So of course, I would like to thank my team members over the years, and we are very, very grateful to the funding agencies because they made ideas to reality and they gave us opportunity to serve. And from my group, I had over 200 HQP, and right now, 26 of them are professors at different continents, including top universities in Canada. And we have actually a few of them, they wanted to become multimillionaires, and we had 4 CEOs as well. And you will recognize why, because we develop also technology. So what I'm doing here is atmospheric laboratory and interfacial laboratories, but I come from physical chemistry, analytical chemistry domains, and I show you how actually we might use different terminologies, but actually the convergence of the different areas of the atmospheric sciences, health sciences, physicochemical sciences can actually provide capability to help Canadians and also human beings more efficiently. So in my labs, we do both applied work and fundamental work. Don't worry, I'm not going to give you too much physics or chemistry lessons. But here, what we do basically, the methods we use, they are through observation, field or remote sensing. We do quite a bit of modeling from molecular scale to 1D and 2D. In my lab, normally we put parameterization for 3D as well. We do lots of cutting-edge experiments through the laboratory work. We have microcosms of different sizes. And during the last 10 years, we developed smart sensors as well as sustainable technology. We develop technology that do not use extra energy, or they have zero net energy, and they are recyclable and are very effective and efficient. And this setup came when I was serving some UN EP reports, and we were leading it, and people were talking from different angles as they were not listening to each other very well. And in that case, we wanted to develop technologies that are sustainable and they can be done. At the same time, they can be very inexpensive so that more people do the right thing for our planet and ourselves. And in the project that we are category of project that we are working, we do quite a bit of heterogeneous reaction, photochemistry, surface physics, and I put the right-hand side, which are more applied for the talk today, because we are doing lots of nanoparticles, emerging material, bioaerosols, including viruses, and emerging contaminants, such as nano and microplastic, and I give you toxic examples today. And also the sustainable technology that I was referring to. So what are our toys? We are lucky to have a variety of toys from high resolution mass spectrometry and as well as very fast femto and picosecond lasers to second harmonic to high resolution FTIR, meaning if you look at greenhouse gases, we don't see how they rotate. They also see that they vibrate. So the vibration rotation at molecular scale as well as radicals become feasible. And we also have facilities for both air and water, as well as snow. As I mentioned, we have mesocosm of different size, as well as a variety of in-situ setup. And we have a numerical modeling, again, based on the computational chemistry and physics to the atmosphere, particularly through the close to boundary layer. And as you can see at the right-hand side, there is a variety of aerosols that we were funded by CFI that are actually very important to do the research, but also it allows us, when we develop new technology, be able to test them in the lab before we send it internationally or nationally. And in that case, it allows us to have a much more accelerated advance in technologies that we might not be able to do without them. So beside these labs, this equipment are not only confined to the labs and or models or making the technology, it is also for the field campaigns. We have been fortunate enough to have been invited in Pacific, Arctic, and Atlantic by collaborators, of course, from Environment Canada to NASA to EU colleagues. And we develop, actually, ask science questions regarding aerosols, oxidants, and so forth. But also we bring our own technology for the field to make sure that we would be able to be robust enough to be deployed, for example, on satellites, on airplanes, and many others. And some of them are kind of fancier than others. This one has gold mirrors, and it can go to 200 meter optical path. So we can see actually very, very trace compounds. And now sometimes we want faster reaction. Those are possible too. We can go femto and picosecond. So what I'm talking about is we actually in the lab, we have the capability of linking variety of processes from angstrom to kilometers, and as well as being years going down to nanosecond and picosecond. So this is a very privilege that allow us to actually explore some of the topics that people don't touch, and as well as something that are going to be very common for and be solution, the ones that I'm showing you here. When we talk about atmosphere, it is actually like a reaction chamber. You have lots of chemistries going in. You can have photolysis, you can have catalysis reaction, you can have interaction with the surfaces, with water, with snow, and so forth. But in contrast to really a reaction chamber, it is dynamic. There is no chamber. It is dynamic. So we can have to actually get methods and techniques to be able to see them as in situ and in real time, because air moves. If you put a virus in air, for those of you who have unfortunately or fortunately, depending on our immune system, have been exposed to SARS-CoV-2, you would recognize that that has also happened in air. And you might have looked at the variety of literature overboard, which is the real mechanism. I love one of them, which is from Germany, that they actually did tests in real cities, and they recognized that people who had wear those masks, they weren't getting as much the disease. So they recognized that air should be the major aspect. And of course, it is very understandable. People, particularly in policy, they don't spell it out. But one of my favorable politician was Angela Merkel, who just opened up. And as a physical chemist, he said, they are aerosol, they are in air, wear your mask, it works. And guess what? People listen to him. And I think that was to her, actually. And that is, I think, is an important thing that we as a scientist, we have to educate our politician to be actually honest, because that's where we can actually bring people together too. And in this case, for the atmosphere that I was talking about, if you recognize, hey, it is not just chemistry or physics or looking at the surfaces or even biogeochemistry, our planet is interdependent. And those are the interactions that become fun from somebody like me. Regarding the aerosols, the big elephant in the room of the climate change, as well as the health organization, these aerosols or airborne particles can have different sizes. They can go from just a couple of nanometers to much higher than. But here you recognize, for example, here you sense your hair. As we go lower in size, you wouldn't be able to see them. And those are the ones that are more numerous. So the ones that are submicron, or we call it nano-size particle, those are by far the majority of the particles in air. And as I will show you, for example, for COVID challenge, SARS-CoV-2 at the beginning is small, is 60 to 80 nanometers. After that, they can uptake water and so forth. They can enlarge themselves, but they start very small. So these particles are everywhere. They are small, they are physicochemical entities, just you and I. So the sizes are different, the chemical composition varies, but they play vital role in variety of processes, not only for air quality, nucleation, climate change, or even health, but it can be actually used in military, cosmetics, sustainable technology, space elaboration, and Earth's ecosystem health, and so forth. So it is not just what I'm pushing you today regarding its importance of the particles. We are actually have variety of implications. So to make it very simple, two processes that we know that we don't know are the processes related to health and the basically absorption and scattering of the particle for the changing of the climate. And as I will be making sure, that is not the only one, but they are made, quite important. But one thing that I want to make sure to keep in mind is when you go around 100 nanometer and lower, that is where nucleation of cloud is starting. When we are looking at very much nanoparticles, when we go less than a micron, those are the ones that actually can enter your respiratory system and so forth. And those are the ones that we have evidence for the adverse health effect. So even though these are very small, those are the key for major processes relevant to climate and health. And remember, when we are looking at the climate change, one of the major uncertainty are actually aerosol and aerosol cloud interaction, direct or indirect effect, that makes a significant information in the estimation, the accurate estimation of the climate processes. I just wanted to bring you back to Earth. This number that air pollution is linked by WHO, 8 million premature deaths. It includes indoor and outdoor, and is air pollution in general, but notably, they actually specify smaller particles. And in urban, actually, we are the major part of the emitters, and we are about 2-3% of the continent, but we have about 50 to 80% of the total global greenhouse gas emission, as well as a significant amount of aerosols. And the cities are also 75% of the energy usage globally. So, and that is a home to majority of the humanity. So what we are looking at, if you want to look at the climatic effort, that is where you can actually cut surgically and have more impact in future. It doesn't mean that we are not going to have impacts in Arctic and the many remote areas. That's not it. But these are the major producers. If we want to cut the climate change, let's cut it right there. You can get much more impact on the investment. So I just mentioned that health organization and climate panel, they actually concur. Normally, these societies, they have very, very different priorities. But the reason they concur that the particles are important is because there are some physicochemical processes are similar to what toxicologists actually referring to: size, configuration, contact angle, surface property, physicochemical processes. So physicochemical lacune that is in here, that need to be studied, and that will give advances in both fields. And I just want to make sure that you recognize that what I'm showing you from the technology is entirely Canadian, happened right after the COVID coming in. And what I did not tell you is that we actually can see these molecules, we can understand the processes, we can remediate them, and we can use them as a technology for other things in a situ and real time, but also in a blink of an eye. Right now, we are about 32 milliseconds, and we are going down as we talk. And the softwares and everything that we develop, with every data, it gets smarter and smarter. I call it actually my baby these days. So I just wanted to make sure that we recognize the terminology that we use. PM 2.5 means particles in air with an aerodynamic diameter of about 2.5 micrometer. It was a very good step for the policymakers to help with air pollution. However, is it good enough? And it is not, to my judgment. And the reason is, the way we measure the PM 2.5 is by filters. So basically based on mass. As I showed you the nanoparticles, they're very small. They're much more numerous than anything else, but they don't have that mass because they are small. So what this one provides us, in some cases, when you make the PM 2.5 lower, the nanoparticles would be lower too, but it's not the case all the time, and it is not what it will be going through it here. So So one thing that I wanted to make sure was COVID was the magnificent, basically, process to let us know that yes, we human that live mostly in the cities are the cause of the many of the health impact and so forth. And this is an example. Here is close to the airport of Montreal. These are condensable particles that are nano-sized. The black one is before COVID, and look at the red one is after COVID, which is significantly lower. That threshold that you see over that is blue, that is the recommendation for how much exposure you should have to these particles. And you recognize, hey, even close to airport, when was it during the lockdown, everything was below the health limit. It was very good. But before and after, that's how it looks. It actually exceeds that limit, which is not very good. And of course, in places, for example, Montreal, because we have approximately 5 months of winter, the boundary layer becomes closer to the surface. And by doing that, we can actually get kind of pre-concentration of pollutant. That doesn't help either. So what did it mean? After COVID, many of the pollutant, look at this one with the nanoparticles, these are nano-size, less than 100 nanometer. They were all disappeared almost, but there are a bit over there, but it's much, much, much lower. And that is where it wasn't COVID lockdown. So we understood that majority of the particles, and we actually did the statistical analysis and they are published. But one thing it means, we are the guilty ones. We are the ones that are causing this health and also the climate effects. Now, what I just wanted to make sure is to recognize, when COVID came in, I had a good friend from China, we had a conversation, and he said he thinks definitely is airborne, and was kind enough to provide us a head start to start making actually some of the masks, developing for the ventilation system and so forth. But the reason we could start was not because we had just a friend, because it was for the 20 years we had opportunity to actually do bioaerosol, and totally by accident. I had a wonderful postdoc who was brilliant, but he wanted to go home. This is a reaction chamber. We were doing kinetics and dynamics studies on it. So he forgot to leave it to air. So basically, instead of closing all of the valves, he left it open and went home. When he came back, the numbers of the molecules that we were looking was very, very, very rapid. Didn't look like hydroxy radical or something that is very potent oxidant. But one thing that was kind of interesting, this setup had optics, and on top of the surface, there was like a gooey greenish color. And when I saw that, I just actually sent it to School of Medicine at McGill, and they just told me, Carissa, you have algae, you have fungi, and so forth. And that was the time that I had just started it. You put a young woman in the 20s at the time, and I said, I put all of my junior chair at the time to understand what it is. And that was a totally, totally high risk. But because of that, we have opportunity to have for example, electron microscopy facilities, access to them, as well as having the technology to be able to look at the genetic scale. We had access to shared green rooms as well, and we were actually taking and writing basically developing understanding of genomic of the snow and air particles. For example, we knew that from a genomic point of view, we knew there is a huge variability. For example, if you go to downtown Montreal to Arctic, and depending on what kind of type of a snow you can get, and we could actually see, there were some nice ice nucleating system that is actually happening, that they change the ice nucleation processes, and it worked very well. But when the COVID hit, one thing that I was very, very surprised was This paper that comes after that, but has basically integrated as a review paper, whatever is what is available. Every single one of them are not in situ. Some were in real time, but most of them, they were not collecting it and then analyzing it in the best way in RT-PCR. We had that. And we knew it is not going to be in situ in real time as they are in air, because these particles move as air moves. The same thing in water. Water is in motion. Particles in water are going to be in motion. Doesn't mean they don't have a stationary moment. Means that it has potential to be portable. And of course, air is a fluid, so is water, but air is much faster fluid than water is. So by doing that, if you want to understand these processes, you need to know what exactly they are and how they move, what the direction, and what kind of changes you do. So we started looking at something that was totally unconventional, and it wasn't there. And when we published it in Nature papers, they said that it's a game changer, it is dynamite, whatever. But it took us about 8 months to get the beginning of the result, because what we were going was something very unusual. I want to go with the cheap, very small lasers like 405. It is visible laser. And it is very small. You can buy it very easily, $500 from India. We can have a good camera, and we had basically we were writing coding and modifying coding of others. And most of the time at the end, we ended up doing most of them to go to nanoparticles. But we were looking at that dark sky to make it to see all of these particles by reconstruction. And it wasn't basically what we were looking at. It is a laser, you go in, you get the samples, you come in. Here, we change the deconvolution. We get a spectrum, and we actually here all together is AI. So what do we get? We don't see them only. You see that these particles come up in and out of the place for you. They see three-dimensional. By the way, Denis, that was the big one was SARS-CoV-2 microcells. And we can get heterogeneity, we can get in real situation, in situ and in real time, but you can do it as a dynamic mode or stationary mode, and we can see single particle or lots of particle together, clusters of them. So what does it mean? It means that if I pick, optically speaking, one particle, I can do single aerosol tracking, or I make ensemble of them, ensemble of tracking, or both. Why do I do that? How we do it? I actually, when I wrote the proposal that was successful, I actually put something like that in it, because that is exactly what AI does. What we are saying, when you first saw Apple, what did you know what it was? From the shape, surfaces, different colors they can have, the taste they have, the smell they have, and so forth. What we are doing here is exactly the same thing. By making the laser system become able to detect not only one direction, 3D, doing the shape, doing the property of the surfaces, intensity, phase, and etc., we are doing the same thing as when you were 5, 6 years old, were able to do. You were able to distinguish from the banana from apple, another one. So in this case, we are looking at how we can use physicochemical metrics to quantify, identify, follow the transport and transformation, as well as usage for the other techniques using the similar technology. And we have actually a portable system. That is where it is. It is portable, and we have the first prototype, and we are doing it after. We said, can we do more, not just for air, just for water? Water for me is easier because I've worked with both systems, and the concentration many times is higher, and they change phases very optically speaking, very simply. So in this case, we started to analyze and measure to this setup as well. And every time we actually use other techniques to check whether or not we're right or wrong. And by knowing how we can actually improve ourselves. Here is an example of a virus that the first time we reconstructed, I felt in love with. It is MS2 bacteriophage. Before we start, I was talking about that some of the viruses people might not appreciate, but these bacteriophages, they can actually stop variety of bacterial infections. They are actually helpful to our system. So in this case, when I was seeing that, I remember the first time I knew that we are going to get SARS-CoV-2 as well. And because we could get the 3D, we could get it 4D tracking, and we had all of those properties, we got them at once. And that was, and actually we would be able to track them, where they are, how much they change, how much they transfer. These are exactly the topics we need for transmission. And as of the few months ago, there was an article in PNAS that they were actually asking, we need that technology, we need the technology in situ and so forth, because we cannot do the transmission, not primary or secondary transmissions. So in order to double check ourselves, of course, and make us humble, we always used also the top STEM at McGill to be able to actually see them, even though when we run it as a stationary and just do it by something that is a stationary, such as STM, which is of course non-in-situ, in real time. But we would see, hey, we are getting it pretty close by, and genomically we were studying, it was the same. We started looking at the transformation, how many of them we can catch at the same time. And that was before we started SARS-CoV-2. When it came in, we had, because we had a lab 1 permission, we have a bioaerosol, but not for viruses. My colleagues at McGill, they were very generous to collaborate and provide us deactivated viruses. And one thing that it was kind of interesting is these airborne viruses, they have a variety of viscosity. And that is where we were playing around with it to see what we can get. And even the activated one, we wanted to know if the software sees only the living one or dead one. No, we can actually see activate and inactivated one. And how it is. I just made it very simple to not make a mistake. So what we did, we did the automation for 2 different things. We can make one as a sensor. It is in millisecond, we can say you have it or not. And you don't need to do anything. You can actually put the sensor everywhere in the room, put it in airplane, put it in the House of Commons, put it in your home. You can actually would be able to do, because all of these setup are run by cellular phone. You don't need to have the data. You have to the data can be remote sensed. And also, it can actually work as a 4D physicochemical tracking, for example, in imaging, in looking at what new viruses are going to come and so forth, because it can say, for example, look at that, it says, no, this one, we mix them up with variety of airborne particles that we could get hand of, and also we test the real air and pushing within the samples that comes in, we can actually detect it very well with over 99%, over 95% of confidence. So we developed a sensor, and we wanted to do even more to see what we can do. Can we do it remote sensing very well from one side to another? Absolutely. This one we do from the home to the lab and so forth. So basically, you don't need expertise as much, as long as there is a center for expertise to get the data. But the sensors can be various in the world, and at the end can get, they can serve together, and they can share the data and so forth, so that we can actually provide solutions, not only for SARS-CoV-2, but also for other incoming viruses, bibecause they are coming, particularly with the climate change. That advice has been given to us from virologists for several decades now. So we would be able to have that possibility. So how does it look like? You don't need to have any difficult samples in your mouth or your nose. You do not, you actually just need to talk. And that was what I did when I had the COVID, and we did the samples ourselves. And the other one, actually, that time that I'm showing right now, at the time I had another virus, and my student had had COVID. But in both cases, we were able to adjust it. And in this case, it was easy. And you're a scientist and you love your setup is non-invasive, just you breathe. The only thing you do, the units, they take care of it. You would be able to actually see them. So I just showed, hopefully, that we can use the particles, nano detection and nano micron, as you see the sizes of the particles. Many of them was nano, some of them were micron. But what about if we use them not only for detection, that we can, also for physicochemical transformation? And in this case, I'm going to be producing a sign that the government of Canada is right now very interested in, and so are most of the world, which is nano and microplastics and pellets that are bigger. These plastic wastes have been identified in air, snow, water. And in snow, one of my students, we developed the technology for the snow analysis to picogram. So we are looking at picogram, which was, and it is till now the highest detection limits that we have. But the challenge for us was air again moves, water moves. Snow melts and gets a different variety of precipitation, consolidation, as well as melting process. But these nanoparticles and so forth can move too. And they can undergo physicochemical processes as well as biological or biogeochemical processes. So in that case, at the moment, there wasn't that. So what we did, because we were doing the viruses, we said, hey, that one, plastic is physically, it's easier. So why can't we store that? And that was, again, because we have already developed all the technology for snow, and we had got to 55 picogram. We knew that we were not going to get that numbers, but we can detect them. And we can get the plastics. And to get the real-time system, we developed and modified our nano-deviation for plastic by making the same classifiers that I showed you, so that you can, you can separate the apples and oranges and bananas. And this way, by doing lots of experiments at different conditions, we make the software smarter and smarter for nano and microplastics. And I have pleasure to tell you that you just look at it, we can go nanoparticles to microparticles, and pellets are easier. We just do some trick that it is, you get it, see it with just the CCD camera, but you can do better in real time using another technique that is coming. But what I'm showing you here, you recognize we developed for these sectors something that can actually give you three-dimensional, because that is very important for the processes. Then we want to look at the physical chemical processes that I will show you in a minute. So in this case, we have the capability, the laboratory capability, and we tested it with the water taken close to Queen's University in Ontario. And what we see actually how they form coating. They, for example, on organic matter or salt or whatever can come on the in plastics, or plastic be eaten by others. But one thing that we find kind of interesting is, and we are still working on it, is to see whether or not we distinguish even not only plastic from non-plastic. We have done it already. That one we have done it already, but how we can actually push it further? Can we see, for example, PVCs from polyethylenes, and which are, polyethylene itself is almost half of the total chemical component of the plastic waste. And it seems to be promising as well. We are being able to do it. So for this reason, when we were doing that one, we just started saying, hey, there are lots of waste in water, such as oil spills that we are hearing, and can we do that? Yep. We can see it very easy. Can we see the toxicants, such as mercury? Mercury is a majestic compound. It has, of course, is a fluid, and it is huge amounts of using for the optical processes. That was for us, fortunate for us. We can actually do something coding. Without coding, we could actually see the phase and intensity to identify it again in 32 milliseconds. And we wanted to do the processes. How can I know what the phases are? How they transfer to something else? How much they have changed the system? What after affects the sedimentation? How much it takes to the forward, basically distribution of the smaller particles? That one we could got it too. And actually we automated it as well. And right now when you're looking at, you remember the uncertainties of the Health Organization and the climate change, intergovernmental panel in climate change. That was their shape, size. I don't get the one size, I get 1, 2, 3 size, 3 dimension, because that it should be. You and I, we are not one dimensional entities. So are the microplastics, so are viruses, so are the contaminants and emerging contaminants. So by doing that, as you can see, we can see the size, we can see the parameters of the system, areas and roughness and many others to provide us to make it smarter. And again, as you noticed, I didn't say 99%, I said it was 95%, because we still have room to improve. And another thing for this physical chemical understanding, particularly meteorological system, or for ice, particularly Arctic ice that is happening, is understanding nucleation processes at much more in-depth level. And for doing that, because there is no understanding of the three-dimensional particles to start with, particularly the smaller particles, we developed a technology that is McGill real-time ice nucleation chamber, which we call it RINC, and 2 of my students have been involved in it. I give also credit to our glassblower, to our mechanic shop and electronic shop at McGill. So what here it is we would be able to understand and decipher where the mechanism is, using a technique that has in the inlet section, three parts, outlet and the chamber, that will allow us to grow the papers and to do it properly. My apologies, I have a sick kid. So I had left my cell phone open. My apologies. But we would be able to understand the processes. So then now I showed you introduction. Now I want to show how we can actually use the nano-DIHM for sustainable technology. So I'm going to put totally a different hat. When we were looking, you hear about green technology, green science, sustainability all the time. Many times when people want to do nothing for climate change, they actually champion it. But not always. Many people with a very good heart, with very good intention, they actually bring it in, bring that green or sustainable technology and science to it. But I just want to make sure, disclaimer, I am one of the green chemistry funders at the beginning for the green chemistry. So I just want to make a disclaimer for that. And I think many of the work are fantastic. But what I would like to show you here is that you recognize that many of the work that was done in the name of sustainability, CFCs was supposed to be clean and sustainable and be less energetic. But because the lifetime cycle analysis was very, very limited, we recognize what happened to the ozone depletion. And thankfully, with the protocol of Montreal and follow-up, it is getting better, but it is not free of fault, because right now in China, they are using chlorinated and halogenated agricultural material that we have to be very, very careful about it, because they can actually react with ozone too. But something we know that it didn't work as well was, for example, when they replace CFCs with CHFCs, because CHFC is a good one, because they didn't really look into the hydrogen reaction, elimination reactions, or can be evidently very important as well. So they goofed again. Plastics that we are using, plastics was supposed to be the Swedish gentleman who made the plastic bags, meant to be sustainable. Didn't think people are going to throw them away, but they did. Or biofuels. and we know what happens to Brazil. So what I mean is, when we started doing sustainable technology, which was about 10, 15 years ago, we started actually operate our labs with solar light. At a time, that was not a sexy choice, but we did choose consciously, because if we want to be helping to the climate change, we better start from ourselves. And our laboratory has been doing it, even for the portable one, the ones that showed you, they are recyclable and run by solar light. But we wanted to do better. We wanted to not use any synthetic material, because as much as we think we know, all of us together are not as smart as the nature is. We wanted to make sure that we use only natural materials, that we actually many times get it from the air. In the one case, getting magnetite particle in air, that we can actually use it as an interface. Don't throw anything in waste, because even though we start with something that is benign, we know what is going to happen next. We don't know every single tertiary and later transformation. And also, I just wanted to make sure that we make sure these materials are efficient and efficacious, and it's cheap, because otherwise nobody's going to use it. So we started, Nermin, who is a professor now in American University of Cairo, she did the most of the work, and the work that was the basis of the elements that of the sustainable technology that I'm producing for you. She did brilliantly to distinguish that the only change of the oxidation of the iron oxides, in this case magnetite, would actually can provide sensors. One area can be good for one compound and awfully bad for another. So basically, it was very distinguished. And by doing that, we started it as a smart sensors. And these materials, because they were magnetic, we didn't need to use energy, and everything was used adsorption. We could use it in water-based and so forth. And we weren't throwing it anyway. We could actually recycling them. And we actually did a bit further for when the recycling of the, for example, mercury-containing lamps and about 9 other metals that we showed it. We actually used these aerosols, these particles, mostly nanoparticles. Those are the elephant of the unknown. They absorb each other. The absorption is very, very gentle. It is very few, just few kilocal. By doing that, you don't need that much to release them. And then you get the absorption, and then using electrochemistry, salt-based electrochemistry, run by a solar light, we could actually get it back. And that was one of the series of the technology we developed for the case of sustainability that were distinguished by a variety of the journals around the world, literally thousands of them. Here, we wanted to actually push ourselves. What about if I remove the electrochemistry altogether? How can I recycle them? And that was very, very difficult. I remember Moinak, who is a professor in IIT in India right now, he was saying, Carissa, can I put something else in it? A little bit of more organic. So I was like, no, let's go stick with that. Let's change it, go that way. And what we did, it was actually, we can actually recycle them. The reaction is about 2 seconds, and with a very high absorption efficiency that we can recycle back again in water-based system. So that was the time that we started looking at, let's put it out in the papers, let's people catch us and do better. Because what the wonderful competition would be, people from everybody else compete for goodness of the planet. And after that, right now, for the city of Montreal, because it is, as you might know, this is it is in Montreal. You see, it looks like as tall as Montreal, and there is huge amounts of pollutant and contaminants in it. We identify a variety of metals, including the toxic metals, and we did quite a bit of work at black carbon that are known for climate change. We developed that techniques that I just showed you and passed it through, and we actually could get variety of metals particularly removed. And it was done in a system, and we used nano-DIHM to see whether or not it is complete or it's coming or which phase they are and so forth. So just wanted to show you that technology, you can have different technologies for different work, but at the same time, sometimes here you have these technologies, they're clay-based, you can actually couple it to nano-DIHM to be able to advance your knowledge. And this advance the knowledge of our humanity. So I just wanted to end with putting the topics that we were getting together. The particle that I talked to you, of course, for aerosol science and climate is very, very important. The nanoparticle and microparticle, they are the most numerous particles, and they are the ones initiating the ice nucleation. And of course, I have to remind people, aerosols are also important in formation, frequency, and intensity of precipitation. They are also referred to be changing the hurricane and so forth. That one I haven't made my mind whether or not I accept it, because they didn't have a smaller particle in it, but there are changes on that regard as well. It is important for the remote sensing that we can actually do it remotely, as well as being recyclable, cloud microphysics of sorts. But I didn't mention to you from pharmaceutical material. For the pharmaceutical material, we can actually do it, and we can do the non-evasion imaging. I did it on my own, my right hand, and to be able to see it by separating setup, we can actually do, for many of us who go through, for example, cancers and so forth. This prototype is not done yet, but the proof of concept is there. We would be able to help people to not go through those tremendously damage, the pain, in addition to the pain that they have, and we can help. And we can also use for the biochemical processes. And as I showed you, it can be toxic metals, it can be nanoplastic, it can be viruses, it can be oil, but we have that Canadian technology to help and help the citizens and around the world. I just wanted to finish my talk with a sentence from Roman. Right now, we are thinking each time that we do a good policy about pollution that can make our life better as something very advanced, very pioneering and so forth. And I just want to make sure that people recognize that air pollution, particularly air pollution, is not something that is new. And it is not new for policy. Indeed, Roman Senate passed 2,000 years ago the air pollution policy, because they were doing mining, and they and many of their doctors, they knew, they had identified that there is a relationship between the amount of pollutant they are doing as well as the health of the workers. And they just started saying, polluting air is not allowed. And that was 2,000 years ago. Our government and other governments on the planet, because we are independent, they have to learn something that Roman did 2,000 years ago and do it like Roman did. And I am delighted to be with you today, and I'm delighted to answer your question, and have a wonderful day.
Thank you very much, Carissa. We will have a discussion and take questions. Anyone who wants to pose a question can type it on the chat, as is our normal procedure. We don't engage in direct oral questioning and discussion here. But while people prepare themselves and maybe take a moment or two to think about a question they might have, after this whirlwind tour of tremendous possible applications of particle characterization, both physically and physicochemically. I'll ask a question, Parisa. There's a few questions, but first I'd like to comment that about the Romans. When Claude Boutron from the Grenoble lab, who was an expert in ice core chemistry, did his first cores of lead in in Greenland, going back to the times of the Romans. He indeed found lead pollution was increasing mostly in pre and post-industrial, but he also did find a peak of lead in Greenland during the Roman times from their smelting activity. So their law didn't
Yes,
necessarily mean that they actually
absolutely,
followed their
yeah,
intention, and
yeah.
that is one of our problems today, right?
Absolutely, absolutely. I fully agree with it. The reason I put it in was at least they knew it. Many of us still, they believe as nothing is happening, and we do the regular life as it is. So in this case, I just wanted to make sure, at least, you know, when one of the wise persons used to say that at least even you know that you don't know is a good thing, at least Romans knew. But I fully agree with you. It is, they knew they were doing badly, and they were right. And the data shows that they were the polluters. Absolutely.
So back to I'll pose my question very quickly. You described a great deal of new technological possibilities that you have revealed through your holographic techniques, DIHM, and others. Have any, can you think of some of the notable technology transfers that are going on where these have led to commercial instrumentation or instrumentation that's being applied in a network research sense or that kind of thing?
Thank you very much for your question. Every time I got a patent, and as soon as a day after proposition, we were getting people who ask for interest. Right now for this one, there are several, two of them has written commitment that they want to use it. I have not given to anybody. Again, it is not my invention. My students are in it too, but also that is a McGill innovation. I am the inventor. But in this case, yes, there are, but I want to make sure that the company would be sustainable. And I also want to make sure that they would be ethical. Those are very important for me because I want to be part of solution, not the future. And I know some of the places they can cut corners. So that the answer is, in this case, yes, the transfer has done for many of our innovations. And sometimes actually right now I am kind of interested for the virus and also for micro nanoplastic, because the companies that are more established, they can bring it to market to be part of the solution faster. But I had done before some of them for the developing countries for arsenic and metals and so forth. And unfortunately, I gave them for free, fortunately for me, because it was my intention to help. But unfortunately, corrupt government doesn't let they want to get the money that comes from it instead of, for example, the women cohorts that I wanted to help because they could have clean water for their families. So in that case, I actually removed that one completely because they were getting discriminating those women and getting the money for by governments that it didn't sound to me very ethical.
Okay, now we have a few questions that I will announce. Anne McMillan asks, you mentioned how important cities are for pollution. Does this technique offer a way to do affordable and accurate monitoring to support air quality policy of the future?
The potential, absolutely yes. And actually, but unfortunately, and I am thankful to be academic because I can say it straight. The government, the level of the governments that they come together, some of them, I'm sure that they are very, very nice people. And actually, all of them are very nice people. I respect them and I know they do the best they can do. But most of the time they go with their mandate, not something at all. For example, you recognize we had very high pollutant air pollution in Quebec for ages and everybody knew it, but they didn't change the law. They didn't make the setup. We have to have more integration of the knowledge from academia and companies and government together, because as it is, has not reached its highest potential. And for many of the, for example, the materials that they look at it, they just, they haven't used it as much. And also some of the items are no-brainer, you can operate it, but some of them, they require systems. So in that case, you need a system that they integrate the data, analyze them, and give it back. In brief, yes, it is possible. Yes, I always, my existence is to help people, other people. So in this case, if I can be of help, I am there and I would be happy to do it. But I want to also make sure, again, sustainability is important, truth is important, and so is the ethical processes that goes through.
You're muted, Len.
We can't hear you.
I shut myself down because my dog was barking. So are you working with any hospitals on applications for medical issues? That's a follow-up from Anne. Yes. Okay.
Yes,
Good.
we are, and we have colleagues. Actually, we are just submitting a paper with the School of Medicine. I was very fortunate. I will just want to contact that we had McGill Medicine, and particularly when we started it, it was totally high risk project when we started it. But now I am becoming more and more confident because I have tried different parts of the human body, and we would be able to do the imaging. And also more than that, it is non-invasion imaging. So the non-invasion imaging, I would say if we have the money for it, we can do it in 3 years. But we have the prototype to give the proof of concept. The answer is yes, absolutely.
All right. And Fred Conway asked, are you saying that this system can detect, distinguish, and identify individual viruses?
We have, yes, for some of the viruses, we have already done that with the, for example, SARS-CoV-1, SARS-CoV-2. We have done for the MS2 from SARS-CoV-1, SARS-CoV-2. That one, we have done it. But in order to be better, and as I mentioned, software gets smarter with every data we put it in, then we have to make classifier for the viruses, and we would be able to do for the larger cycles. But I'm actually on another domain as well. We are coding another type of the characteristics that would be important for viruses, because viruses, they have a beauty that are extremely easy material from a phase point of view and viscosity point of view to detect. It's very rare, that type of composition. I worked with bacteria before and many others. There is a huge variability. But there are, again, if the classifier becomes working, it can be providing. So it is not the question of science. The science has shown we can separate SARS-CoV-1, SARS-CoV-2, MS2 bacteriophage. But it is the fact that we have to do lots of experiments to get the data, high data, and to decrease the uncertainty.
The devil is in the application.
Yes.
One question we have here from I think our webmasters: how interested are governments in these advances? You touched on this a little bit.
Yeah, this one, again, for I have not sent the proposal for the government at the moment. I have to give for the NRC has supported the nano and microplastic transformation, and I'm grateful to them, and I had put the num in it. But so I have not actually sought any government, like a federal government or so forth, for the innovation. However, we have sent it, for example, all of the papers we get to the city of Montreal, to the government of Quebec, to make sure that they are aware of it.
Good. Well, I think our questions are no longer. We've come to the end of our questions and our time, I think, as well. And so I'd like to just end by thanking you very much for a wonderful multidisciplinary introduction to another discipline. Meteorology and ocean science we represent, to a subject that touches on many aspects of our issues and problems, Parisa.
Thank you very much.
Oh,
And I
yeah.
wish everybody have a wonderful day.
Yes.
Thank you for your invitation. Have a good
Thank
day.
you, Parisa. Before everyone goes, I will just remind you that we will keep in touch with the CMOS Ottawa Centre website. We will have a talk in January to be announced, and another one in February by one of our executive members, Dan Shan from our RMC. So keep in touch with that, and all of you have a wonderful holiday. Thank you very much.